Welcome, everybody. We're going to be working on Unit 7 this evening. During the past 2 weeks, we've been looking at supervised learning in two parts, right? And if you think about the underpinning of what that was, supervised learning is where we start with data, basically, that is already labeled for us, right? Unsupervised learning is working with data that's not. And if you think about the real world, that's how most data is. When you first encounter it, you don't have a label for it. You just have raw information. So there will be a part 2 to this. Tonight, we're going to be focusing on two critical approaches to doing unsupervised learning. And one is the k-means clustering, which we might consider the most fundamental form, and then the DBScan. And then next week, we'll look at some other methods. I am going to be working off of the Intel provided PowerPoint here, which is shared in the course shell. So I'm going to bring that up on screen, which I'm doing right now. And of course, it goes to screen number 2. I'm going to go into slideshow mode, do my standard flipping of screens and arranging, and I'm going to get rolling here. Feel free to ask questions along the way. And here we go, folks. All right. These are the topics we're looking at, and I think I just mentioned all of these. So let's dig in here. It is really critical, right, that we talk about this when we start talking about the differences between the supervised and unsupervised machine learning models. And the fundamental aspect of it really boils down to the fact that we have data that's labeled or unlabeled, and there is a difference between that type of information. Data in its raw form is information. So for example, if I could, I don't know, plug into the computer of my car and read the data that it was generating as I was driving and just looked at it in its rawest form, which might just be a text file or something really primitive, or a tabular data file that's just got a bunch of numbers in it, or 1-0 flags or true falses or something like that, I would look at it, and without it being organized, it's just information. What really gives data value is when it becomes structured, right? So that's pretty important. And the primary way that we structure data is in a tabular format. We've talked about all these concepts before. So when you put things into rows and columns, it goes from being raw data to becoming information. It's something that we can use to do other things. When we look at a table of information, typically the way that a table is arranged is that each row of information is typically related to a singular entity or transaction or item or event or something of that type, right? So for example, they're giving the example of if you have a data set about pets, that each row in a table might just refer to each unique pet that you have, if you have more than one, right? And then the columns within that table would be based on the different features of the pet, what species it is, what's its name, when's its birth date, what are its characteristics, height, weight, size, whatever, those types of things. When we start looking at, the different data points for each entity, right? So if you think of pets, in this case, they're looking obviously at something else here that looks like job positions, experience levels and whatnot, and salaries, right? And I do want to just tell you guys that you look at this list here and they say all these salaries are over $100,000. And granted, they're in New York City, but is that what a developer can expect to make when they're working professionally? Is that the kind of money you might make professionally as a developer, if that's what you become? Yes. Yeah. The people that work in IT can make really good money, and I might even say that these might be starting salaries in New York. Right. Okay. So we're not really examining the data, but the point is that when we look at the columns of a table, so like the position, experience, whatever, we call those the features. They're like data points relative to it. And one of the columns we're considering the label. Like, what is the key piece of information in that table? Like, what are we looking at? You know, maybe if we were looking at pets, the label we'd be looking at is the species: cat, dog, frog, fish, parrot, that kind of thing. Um, so these would all be features, but the label, the salary, is in the label column. And so what is a label then, right? So what do labels mean? It says labels are the outputs we're expecting from the machine learning model. If you look, for example, at like the simulated Fitbit data that we were looking at, that I generated, when I asked ChatGPT to generate that data, by the way, I had to make really careful indication that it should not just give me the raw numbers, but it should also give me a column that indicates whether the person is okay, basically. Are they healthy, not healthy, stressed, or whatever, oh, you're dead, sorry, that kind of thing. And that really in that data set is the label. Is that, are they healthy or unhealthy? That type of thing. It says in the pet example, labels may be the species of the pet name. That's what I was saying. Here, it would clearly be the salary. And why are we looking at that? Because that is our target output thing. So for the Fitbit data, we're looking for health level. For the pet, we're looking to see what species it is. For the developers, we want to see how much money they're making. So that becomes the labeled data in that data set. Now, when we're looking at unsupervised learning, we need to start with this concept, unlike the way that we normally learn as human beings. So like, for example, when we're a child and our parents teach us the difference between a dog and a cat, they're labeling it for us. They go, look, that's a dog, that's a cat. It might be a picture in a book, or you might have one in the house, right? And you can see a cat looks different than a dog, behaves different than a dog. They're different size, different fur, whatever the case may be. But when we start to look at the comparison between the labeled and the unlabeled, if you were learning what these things were and you started with no labels, how would you figure out which things are similar, dissimilar, or what we're looking at? And notice the labeled data can be different things. So it can be the species, or it could be some other piece of information. In this case, we're looking at weight, right? That's the labeled data, if that's the target. But it is, relevant, right? It says here in the field of machine learning, unsupervised learning refers to learning without a ground truth such as labels to correct the error your model makes when guessing. Okay, so that's very different. So if you weren't told what a dog and a cat was, like you just landed on this planet, you've never seen one before, you go, well, those kind of look the same, and those kind of look the same, and that one looks way different, and that one I'm not really sure, that kind of thing. So we can still apply algorithms, though. This is what's interesting about this. To make a guess, it says about the distribution of the data based on a sample, then checking its guess against the actual distribution, right? So then you can compare, like, well, I have this piece of information and this piece of information that I've processed, and this piece of information is like this new piece of information or the old piece of information. We're looking for correlations. It says, unlike supervised learning, we're working without a labeled data set. Okay, we said that. It says, given the scarcity of labeled data in the world, right? So this is why it makes sense. The corollary that supervised learning cannot be applied to most data, and the fact that models learn best when trained on more data. So the fact that most of the world gives us information, or we gather information, that's not labeled. Like, we collect information from nature, where it's not telling you what it is. We're just gathering the information, or we're looking at pictures of like space, and we're gathering data on that. We have no labels to tell us what it is, right? So and I think this is a profound statement, the last one on this slide. It says the future of in large part of AI depends on getting better at unsupervised learning, right? To be able to organize, classify, and ultimately, I guess, label data that comes in unlabeled, because most of what we will encounter in reality will be that, at least initially. All right, so they start to use the example of Netflix to drive this, and I think this is kind of interesting. So they say, how does Netflix work? So if you've ever watched Netflix, or really kind of like any of those types of streaming services, depending on what you've watched, like, so for example, if you watch a lot of, let's say, reality television, there's a very good chance that Netflix will recommend something for you to watch next that's sort of similar, right? Or if you like comedies, it might show you a comedy. Or if you like, I don't know, a romance show, it might show you another romance show. You like action or sci-fi or whatever it is, right? And but how is Netflix making that determination? How are they determining what you might like? And how are they, what's their algorithm? Okay, well, I guess part of it, you could say, they have their TV shows labeled. So if you watch nothing but comedies, they're going to find everything that's listed as a comedy and play it for you, right? But their point is, they really don't have anything to base the predictions or recommendations on, right? Instead, what they look at is other users who've watched what you've watched and what they watch after, right? So if you watch, like, I don't know, WWE on Netflix, and then you watch, I don't know, some action adventure thing, they might recommend, like, if you watch WWE, they might give you the same thing. Or if all the WWE people would watch that and then they watch, pick something, then they'll recommend that. So what they're doing really, and this is their strategy, is they're clustering the users based on similar interests and really behaviors, if you think about it, right? Simply clustering observations together based on similarity, hoping to make accurate conclusions based on those clusters, right? So whether you like what Netflix shows you or not, and I always have this issue when I look at these streaming services, and it's like, man, they always show me the same stuff to watch. There's got to be other stuff out there, right? So then I start doing deep dives and doing searches and looking for weird things. And sure enough, if you watch something that's kind of different, then they start recommending different things. Like, and if you have a household where you have multiple profiles on your streaming service, compare what your feed on that service looks like compared to somebody else in your family who has different interests than you. I think it's very, very telling of their algorithm. So let's look at an example here as we go and start talking about k-means clustering. So first of all, like, what is clustering? So they're calling it says the most common exploratory data analysis technique. And what we're doing is we're trying to get basically some knowing about how this data is put together, right? You can define it as the task of identifying subgroups in the data such that data points in the same subgroup or cluster are very similar, while data points in different clusters are very different, right? By whatever criteria, that data is being classified, right? So it says, in other words, we try to find homogeneous subgroups within the data that data points in each cluster are as similar as possible according to a measure such as Euclidean-based distance. So here comes the distance formula again, right? And you thought you'd never use it again. Or correlation-based distance, which is, roughly similar. Now, which of those approaches you use, it depends on the application, right? So like, you'll have different types of data, and sometimes straight up regular distance formula works and sometimes not. But generally what we're trying to do is, like, if you're clustering stuff together, well, this stuff's all the same because it's all kind of in the same area. So if you're within a certain distance of that, you're in that group, right? It's kind of like, all of us are clustered together in Wisconsin, so we're all Wisconsinites. We're all the same, right? We're all Packer fans, right? That kind of, it's that kind of thinking that goes with it. Now, what do we use it for? And there's lots of uses for this, and it's used quite a bit actually, because this is one of the k-means clustering in particular is one of the more fundamental approaches to doing this. So they use it for market segmentation. They try to figure out what customers that like certain things are in terms of their behaviors, right? So in other words, like, hey, if you like cheeseburger, fries, and Coke, chances are you're maybe not a salad eater, that kind of thing. Or if you always eat salads, maybe you stay away from the burgers and the fried foods, that types of things. So um, they also use it in image segmentation and compression, right? Where they try to, like, if when we transmit images over technology, some of them can be so big, and this is how video streaming works too, where it's like, hey, that whole area of the sky is blue and basically the same color. We can compress that data and transmit it all together and then paint it back all as that color, right? Rather than looking at each individual pixel, right? So that's sky, that's ground, that's humans, that's grass. Those are all clustered together, right, in images. Um, Also, like when we look at like documents or even text, that stuff is also clustered sometimes based on the type of information that it is. All right. All right, so let's look at this first algorithm, the k-means clustering. I want you to look at some of the terminology as we go through this. What we see up on the screen there in terms of a graphic is an example of a k-means clustering output, right, where the data is grouped by color into various clusters on the screen. And this is done basically with algorithms, math, and usually a programming language or tool, right, to kind of get this sort of representation. It says here that the k-means algorithm is an iterative algorithm. Iterative in programming, right? So just to refresh your Python skills, iterative means a repetitive algorithm. So in other words, part of the process of doing this is you run the algorithm, you run it again, you run it again, you run it a certain number of times in order to get better results, right? So it says it's an iterative algorithm that tries to partition the data set into K, or predetermined number of non-overlapping clusters. So you might decide that I need 2 clusters, or I need 6 clusters, whatever that number is. And that's what we're talking about. Every situation is different, and it might not make sense to have a whole bunch of different clusters, and you might only need a few, or you might really need a bunch of different distinct ones. But ultimately, each data point will belong to one cluster. It can't be like 2 clusters. And even though some data points are really close together, they have reasons why they're part of one cluster and not part of the other. And there's algorithms that do that. It also tries to make the intra-cluster data points as similar as possible. So what's intra mean versus inter? You guys, like, what does the interstate do? It takes us between states. And if I did an intra-state, that means within one. So in other words, what they're trying to say here is the points that are within a cluster of the same color, these should be as similar as possible. Now, you do notice like the purple one's got a few that are kind of like way out here. Maybe it could be green, right? But mostly they're purple, right? Then you got these that are kind of on the cusp of being yellow, but they're not. So, but at the same point, while they're trying to do that, we're also trying to keep the clusters as different as possible at the same time. So they're clearly defined, right? So that there's no question where it sits. Some of that is revealed in the dimensionality of data. Like we're looking at a 2D plot right now, and maybe if in a 3D format, it would be a little clearer what the delineations are. They might not seem so overlappy there. Or if we could visualize more dimensions than that, it would also help. All right. The other thing that it does is it assigns data points to a cluster such that the sum of the squared distance between the data point and the cluster's what we call centroid, which means the mathematical mean of all the data points in that cluster is at the minimum. So in other words, it calculates, like, let's say this purple blob or yellow blob, where the center of it is mathematically. And how they determine that is they look at all the data points in the cluster and they try to minimize the distance from all the data points collectively to the center point. Now, in the process of doing that, it also recalculates the center point at the same time and might even do reclustering. And this is kind of what this session is about largely. And that with every iteration of the algorithm, it tightens up and it moves and it becomes more seemingly accurate. And it says the less variation we have within clusters, the more homogeneous or similar the data points are within the same cluster. In some cases, there's questionable areas, but when you see the colors, yeah, you can say, okay, well, here's all the green and the center's probably here somewhere, and we're minimizing the distance of all the points to that center point, and it forms that cluster. I'll just kind of reiterate some of this. Now, this is an animated graphic you're seeing on the screen right now. And what you're watching is you'll see that it's going through its iterations of running the algorithm. And as it starts, the little stars, which are the centroids or the center point for those clusters, start in one spot. Where does it start? Kind of arbitrary decision point, right? And that's part of the algorithm, is it figures it out. And as it runs through each iteration or revision of the algorithm, it moves that centroid. And after you get to a certain point, that center point should move very little. It should get really to where it's supposed to be, right? And if you notice, like the green one very quickly gets to the center because its data is very defined. And then the blue one takes a little while, and so does the red one, because their data is more scattered. And as they're going through the iterations, some points which were blue become red, and some, so some jump clusters, right? And that's determined by the math, because the math revises the centroid, and then the centroid is being in a different spot. Like this red one moving down into the left a little bit then starts to include some of these blue ones, because the math works out that they're closer to this centroid than the other centroid. But basically the way that this works is we're trying to minimize the distance to the nearest centroid mathematically, right? And if you think about like what it takes to calculate the distance of one point to another using the distance formula, well, what if you have 40,000 data points and you're trying to minimize a whole bunch of them to a centroid? So this is the math that happens. And this is why we don't do it with pencil and paper or calculator, because you would be here for days doing it. You use spreadsheets, you use programming languages, you use computers, all that stuff to accelerate the workflow. Okay, so let's review how the algorithm works. It goes like this. We decide how many clusters we want. That's the K number, right? So in this case, with this example, there's 3 clusters that we want to find. So there's therefore 3 centroids, right? So we initialize the centroids by first shuffling the data set and then randomly selecting K data points. That's really kind of weird. You're randomly selecting it? Yeah, right? And so you're randomly selecting K data points for the centroids without replacement. We keep iterating until there is no change to the centroid. So in other words, we keep running the algorithm that calculates where the center is until those centers stop moving. And then we know that we have them in the right place. So think about this. The more times it iterates or repeats the algorithm, the more accurate that will get. But there is a point where it runs so many times and it will be accurate. This is why this is one of those primary algorithms that you use for clustering, is because it works so well. Now, this is kind of an interesting graphic too, as you watch here, because we randomly select the data points. You notice how just look at the red one, for example. It starts out up in the yellow area, right? And then as it runs a few times, it's like, oh, I don't even belong here. And it moves down to the red area until it finds its spot. And I'll just back out of the slide and come back just so you can see the animation again. But notice how as it iterates, it gets all the centroids get to the right point, and then the classification or clustering is a lot clearer, right? So What's happening in the background, and mind you, we do this with Python code. We don't do this manually because it would be here forever learning how to do the math. We're using the tools, high level tools to do it. It computes the sum of the squared distance and all the points. It assigns each data point to the closest cluster, whatever the closest centroid is. As we keep recomputing the centroids, we're basically just taking the average of all the distances of the points around it and trying to make it so that the combination of all their distances to the centroid is as small as can be. That's the whole algorithm. And it's done by averaging those distances and then minimizing them. Now, if you think, and I just want you to think about this, the energy and thought it takes to calculate one distance formula, even though it's a mechanical process. And if you had even just a few hundred data points working around 3 or 4 different clustered centroids, how many different equations you have to run simultaneously and iteratively in order to calculate that? We're talking about thousands and thousands of calculations. And that's why we hand this off to a programming language and a computer system or a spreadsheet or whatever, because those tools can do that process very quickly rather than us sitting here for days and weeks and months calculating it mechanically. Not that it's not possible, it is, right? But that's why we use the technology. All right. So now that we kind of have an understanding, let's start to look at a couple of examples. And this is where it gets even a little bit weirder, because now we're looking at what we'll call tangible data points. Now we have 4 different objects, let's call them A, B, C, D. Each has an X1 and an X2, or 2 data points, 2 features that we're looking at. You could treat these as an X and a Y on a graph if you wanted, but that's not really given information. But these are our observations. So we've looked at this information. The information's not labeled. It's just raw data, and it gives us the X1, X2 values for each one of these. Okay, 4 data points. All right. First step, okay, look at the data, right? Then we arbitrarily choose 2 centroids. Now, how do we do that? We take, I don't know, 2 of the data points and we combine them. So we're combining A and B and C and D, and then we're choosing the average or the distance between them. So for example, if this is an X and a Y on a graph, and this is an X and a Y on a graph, we can find the average or the middle point between those 2 points on a graph. So like if I did it visually, you totally see it. I just put a dot on the screen, another dot on the screen, and go, hey, the middle's right here, right? But you can do that mathematically too, right? And that's what the distance formula is all about, right? So A and B is the average of AB, and CD is the average of C and D, or basically the middle point of them. Then we apply the distance formula. And once again, don't freak out to the look of the mathematical equations here. What this basically says, if you remember the distance formula, it's A squared plus B squared equals C squared. And then if you want to solve for C, it's the square root of A squared plus B squared, right? And the distance in between them. Okay, all that stuff. And then this big sigma is the sum of that, and we're trying to ultimately minimize it. So they go through and they calculate the average points of A, B, and C, D, and they come up with different points, right, which are now the centroids, and then they run the distance formula on them, and then they start to iterate. All right, so they go through like a whole basic like proof here. It says if we observe the highlighted distance between point A and this centroid. So now we're taking each individual point and comparing it to the combined or center that we've developed. We notice that the distance between A and the CD thing is 4, and it's less compared to A and B compared to A. So in other words, this number is higher than this one, so A belongs to that one, right? And then B belongs to this one, C belongs here, D belongs here, right? Because the distance is smaller. So that just based on that distance, right? We are clustering. And that's really the algorithm. So what happens then is it goes through an iteration and we go, oh, A, C, and D are really kind of clustered together, and B is kind of on its own. And so it'll keep iterating until it boils down to that. But this is a super simplistic example. Now, can you imagine if you expanded that to dozens, hundreds, or thousands of data points and you make those same comparisons? And so just mathematically, you can determine that, right? Now, because it keeps iterating, right? We still keep calculating all the individual points compared to the clusters that form. So every time we iterate, we're forming clusters. And now we have this B cluster and this ACD cluster, and then we're still comparing the individual points to it. And as we keep going, what'll happen is it'll just show more clearly over and over again that one is clearly the correct cluster for it. And it just kind of keeps iterating. It keeps running, and it says all data points are ultimately assigned to clusters B or ACD based on their minimum distance, and the iterative process ends here because we have got it to the point where the values stop changing, and therefore we know that the centroids are correct and in the right spots. Right. This is not magic. This is not guessing. It's all math, and this is what's so cool about it and why math is such a powerful tool. Now, interestingly, we started with a K number of 2, meaning we're trying to form 2 clusters, therefore 2 centroids, and we're doing that math comparing to those 2 things. So the K number in this example is 2 clusters. It's predetermined. Who told us to do 2 clusters? Well, I guess we did, right? Or the PowerPoint told us to do it, right? And in some cases, you look at data, you plot it visually, and you go, there's clearly a cluster here, clearly a cluster there, and it's very obvious. Sometimes it's not, right? It doesn't seem like it is clustered at all. All right. So we are going to watch this little video here. This does have an alternate name, by the way. They call this Lloyd's algorithm. And it says with the increasing iterations, the number of data points assigned to the clusters are increasing. So now this video, I think, if I'm not mistaken, I think this one does not include any verbs or words, but it might have music. So I might mute the music if that's the case. So just be mindful. Okay, so this is the one with the music. And so I'm just gonna restart it and I'll just kind of read it to you. So we got a K of 4, 300 data points. We randomly select centroids. Notice how far off they are from the apparent clusters. We're assigning data to the centroids, and then we calculate the differences. Then on the next iteration, the centroids move, and we recalculate all the points with the same color. Points move, some points get reclassified. So we're on the 3rd iteration right now. Centroids are moving, not very much that time. I don't know if you caught that. 4th iteration. Tiny little movement in a couple of them. Iteration number 5. Another little bit of movement. And then we're going to call this convergence. So convergence is where the centroids really basically stop moving. And then we have clearly defined clusters, clearly defined centroids. And this data came in unlabeled, right? So this is kind of the point of how this works. All right, pros and cons of using this approach, right? This one is pretty simple to implement. It works really well with large data. It guarantees convergence. Why? Because the math forces it, right? And And that's the beautiful thing about it. It's kind of fudge proof in that regard. Um, you can warm start the position of centroids. So you can kind of put the centroids where you think they belong, or you can just kind of randomly put them in and they'll still find their way. It Once the model is trained, it easily adapts to new examples because it's using math to kind of drive it. And it generalizes to all sorts of different shapes, sizes, dimensions, and mathematical formulas. So, for example, if the data is like tightly clustered in a little ball, it works. If it's elliptical and flows around other data, it works. If it's on a straight line, it works. Great. All of those are good. So that's one of the positives about it. There are some drawbacks, right? And they're listed here. And it says, if you choose K manually, like how many clusters are you forming, you have this what we call loss versus clusters plot to help guide us. Like how many clusters do we need? Well, it depends on kind of basically the how far the points are from all the centroids and how many points we have total to calculate. And so what they're telling you here is that there's how much of a loss there is versus the number of clusters. So, there is a scale basically that's mathematical, and you can tell it's a curve shape, so it's probably logarithmic that it's happening that way. Centroids can be dragged by outliers, or outliers might get their own cluster instead of being ignored. So this is maybe one of the weak points of it, because you're trying to like take stuff that's way on the perimeter somewhere that might not fit and force it into fitting. What might be helpful is to actually just either remove those data points or form a new cluster is what they're telling you. The scaling with the number of dimensions can be an issue as well. And it says as the number of dimensions increases, or number of data points per row, a distance-based similarity measure converges to a constant value between any given example. So in other words, you can't really focus on too many feature sets at the same, distinctly at the same time, to make your classification. I'm either worried about the pet's weight or its species, because I can certainly get cats that are fat or dogs that are thin, right? Where the weight crosses over. So I can't determine if it's a dog or a cat just based on weight. Right. And I've had a dog that was as little as 7 pounds and a dog that weighed 150 pounds. Right. I've never had a cat that big though. Right. So chances are of me finding a cat that's 150 pounds is unlikely. 20 pounds, maybe. Right. But you see my point, right? And that's kind of the aspect of it. All right. So the k-means function, when we start to code in Python, and this comes from scikit-learn, right? So that's a library we've been kind of playing with recently. It has tools built in for doing clustering with k-means, and it's got a number of different parameters. And you can see here that they call it 8 tunable parameters. Now, when you write computer code, when you do a call like this, k-means is a function that's part of this library. And then you see the parentheses, and the stuff that goes inside the parentheses are values that we are sending to the function to process our information. And these are basically settings, kind of like if you sit in the car and it's like, well, the heat's on, the lights are on, the wipers are off. Those are like parameters for a car. These are parameters for running this function. Some of the key ones for us are very simple ones. Like we won't necessarily need to tweak all of these when we run the code. We will target very specific ones, usually based upon what we're told in the instructions. So for example, in the Unit 7 homework, I ask you to change the K number, which is the number of clusters. So if I'm asking you to put in 9 clusters, you change this number to a 9. If I'm asking you to do 3, you change it to a 3. And that'll change how many centroids you have and how many, calculations are happening and all that type of stuff. Max iterations, for example, is how many times it'll run through that process to try to narrow down the centroids. That's a controllable number. Whether or not you want to tweak that one, that's relative. But it has 8 tunable parameters, meaning you can change these to other values depending on the kind of thing that you're doing. Normally, the thing that we change the most is the number of clusters, by the way. All right. Now, it all right, so this is what they're pointing out. So the n clusters equals the number of clusters that we're going to run. The algorithm by default, if I include it in my code, will default to a set of 8 clusters. Why? I'm not sure. Somebody arbitrarily chose that as a good value for most data sets. That might not be what we need, though. If we're classifying dog and cat, 2 is good. Right? Yeah, absolutely. All right, so that's the one value. Another one that I pointed it out before is how many times do we want it to iterate? The default number of iterations is set to 300. That might be excessive, or depending on the data set, might not be even close to enough. And this is a tweakable value. There are ways to take the syntax of this statement, by the way, and narrow it down. So it is possible, if you wanted, to take the k-means function and just feed it this little bit of information. You see where the arrow is pointing, where you're just declaring the clusters and a random state and then forcing it to run. I forget if like what format our code's in. I think our code's in this format. So when we make our tweaks, we'll tweak it here. But there are shortcut ways to do it as well. Sometimes when a function has a large list of parameters like this, like tweakable things, you don't need to, and they have defaults, you don't need to send them all in. It's probably a good idea, but if the default is 8, I don't have to say it. That's the thinking. Okay. Right. And then ultimately what they're trying to show us here is that you can, if you structure it right and you know where you're going for it, you can really streamline that code down to very little and do some very powerful stuff with a very, very small amount of code. All right. We are reaching kind of the halfway point here. I think we should take a break. Let's do a 5-minute break. We'll come back and talk about the other methodology. So let's do that. We're going to pause the video here, and I'll see you in 5 minutes, folks. All right, we're back from break, and we're going to press forward with the material, and we're going to look at another technique that's called DBScan. And what this acronym stands for, and I love the little animation here, is density-based spatial clustering of applications with noise, right? This is also a very popular algorithm for unsupervised learning, and it's not just used for machine learning. By the way, it's used for other things as well. But I like that they build a face out of the clusters. I think it's kind of neat. But sometimes data takes really weird shapes, right? And it says that this is a method that's used in machine learning to separate clusters of high density, things that are really close together, from clusters of low density. And it says because this is a density-based algorithm, it does a good job of seeking areas in the data that have a high density of observations versus area of data that are not very dense with observations. It doesn't necessarily say it's ignoring them, but it clearly is saying, okay, there's a lot of data right here. Why? Why is it there? That's kind of the approach. The way that it operates is it divides the data set into a certain number of dimensions, and n is basically a variable. We don't know how many that is. And as you look at this graphic, you see that what is it highlighting? It's highlighting larger clusters of information, things that are clearly grouped together in an area, right? And it's kind of ignoring the stuff that's not. It says for each point in the data set, DBScan forms an n-dimensional shape. We don't know. So it could be a square, it could be a circle, it could be an ellipse, it could be whatever. And then it'll shape, right, n-dimensional shape around that data point, and then counts how many data points fall within that shape. So it like is anticipating what the shape is, and then it counts the data points, and then it figures out how many other points aren't within it, right? So it counts that as a cluster, and then it keeps expanding the cluster by going through each point and comparing it with other points that are basically nearby to see if they might fit in the cluster too. Right? That's the general approach of the algorithm. And they say they have like a little visual example here. So let's take a look, right? It says that as you notice from the graphic, there's a couple of parameters and specifications that we need before we let it do its work. So there's, okay, a couple things that we have to figure out. What's the minimum number of data points needed to determine a single cluster? Like how many put together makes it significant? 2? 1,000? How close together, right? And how, right, so how far away can they be from each other as well is a big part of it to still be considered part of the same cluster. All right, so these are kind of interesting things. So if we start to look at this in terms of graphics, right, it says, what is the minimum number of data points needed to determine a single cluster? And it says the minimum number of points needed is set to 4 in this scenario. Okay, so it says when going through each data point, if it finds 4 points with an epsilon distance, and that is from the point to like the range of where it's fitting into, a cluster is formed. And as you can see with some of these down here, some of these, let's say like this data point's got this circle going around it, you'll notice that there's 4 other data points inside of its circle, right? So they make sense to be clustered together. We also asked the question, how far away from one point can one point be from the next point within the same cluster? And that's why they determine this radius. So in other words, like if they determine that this is the epsilon distance to the circle, and they do that with all these other points around here, you start to very quickly get these clustered together. And you can see how the yellow ones kind of sit as outliers a little bit because they're not, well, they might be inside this circle, but they're not inside the others, where all the others are kind of overlapping within their own circles, or for the most part, they are. All right, and they have like some examples. So they have a noise point, and this is kind of interesting. That one doesn't get assigned to a cluster in this scenario. That's way out there. Doesn't seem to be part of this gathering. So we're just going to ignore it. We're going to call it noise, whatever. It's a weird, we're looking at dog, cat, and that's a bird, maybe, right? It's not even a mammal. Who knows, right? The yellow points, what they call those border points, still part of the cluster, right? Because it's in one of the circles, right? But does not meet the minimum points criteria, which means how many other points are in the same range, basically. Right. All right, so this is a catch to remember. It says, in order for a point to be considered a core point, it must contain the minimum number of points within epsilon distance. And that's what that number is about. So how many points are we looking at? 4. Right? The point itself is included in the count. So whatever you set as the point that we're measuring from, that's part of the 4. So we just need 3 more, is really what that's telling us, right? And if we're looking for 4, we just need 3 more. Right? They do have documentation here, and I think it's kind of worthy to click on this because a lot of these libraries are like this, by the way. So scikit-learn has a whole website dedicated to it that talks about all the different things that happen, and they talk about how the code works for it. They show you the parameter list. They talk about what each parameter means, how to set it, et cetera, et cetera, et cetera. They give you a lot of details about this. The other thing that you'll notice is some things are considered parameters and other things are considered attributes, right? And parameters, mind you, are things that we feed in, and attributes are information about that information, if you will, sort of like metadata in a way. Okay, so, and they're looking, and what they want you to look at here in particular is the min samples parameter. Let's just go back there for a second. And it says the number, and I want you to notice here that it's the default is 5, by the way. The number of samples or total weight in a neighborhood for a point to be considered as a core point. This includes the point itself, right? So we talked about that. And if the minimum samples is set to a higher value, DBScan will find denser clusters, whereas if it's set to a lower value, the clusters will be more sparse. But if 5 is the default, you can see that if you want stuff to be more dense, a higher number is going to help you. Okay, so that's kind of the point of it. And so like if you were a data scientist or an AI engineer or whatever, and you're trying to engineer this stuff, these are all little things that you play with and have to understand how these algorithms work in order to tweak your models and get them to work the way you want them to classify that unlabeled data. Okay. So why is this maybe a better tool than the other approach that we're using? Now, the other approach, right, was using the distance formula. And you know what? It makes a lot of mathematical sense. You know, if this information is all clustered here and this is all clustered there, they clearly are related. But what if the data is really kind of weird, like the data we're seeing on the screen here? So in the left image, we have these data points, and you can see they're clustered. There's gaps in between them. But if I was to run the k-means algorithm on this cluster, it might separate this group up here from this arm down here. But what DBScan allows us to do is it can go, no, this is all one shape. And this is all one shape. And this point might be closer to another point than that point is, or whatever. But it's identifying the distinctions regardless of the distance, right? It's using a different algorithm, right? So it can, so in other words, DBScan can adjust both shape-wise, but it happens via the dimensions in order to find similar clusters, kind of like the way our eyes are doing it. Our eyes are looking at it and going, yeah, this is all one big blob here. These probably aren't part of any of the blobs, right? Or they're kind of outlier blobs or whatever, but we see it with our eyes, and DBScan gives us clusters more similar to what we see with our eyes, I think, right? And I think that's good to know. All right, so advantages of using this approach. It says it's great at separating clusters of high density versus clusters of low density, right? So if you have significant groupings in your data, that's what it latches onto. Also, because it's good with handling outliers within the data set and sometimes excluding them, but it can contend with them, right? Rather than in the other scenario with the k-means clustering, and like, let's just remove that one and not even count it. You know, that's a bird. We won't even look at it. That's kind of the thinking. But this will deal with the outliers maybe as a grouping. One or a couple of reasons not to perhaps use this. It's good at separating high density from low density clusters, but when the clusters are kind of the same density, like if all the data is kind of like equally spaced, then it doesn't know what to do, you know, politely, right? It's less clear on how to organize the information. It also doesn't do really well if we have lots of dimensions in the data or lots and lots of features that we're looking at, right? You know, and it's partially because how the algorithm works. So like it has a useful, you know, limit, so to speak, depending on the number of dimensions, but it works best with stuff that's clearly highly clustered. This, like the k-means coding, has a bunch of parameters, right, that we feed in. And this one also has 8 parameters, but it also has 5 attributes, right? And we were talking about this sort of briefly. All right, so this one's asking me to verify I'm human. All right, great. What's the difference between an attribute and a parameter? An attribute is a variable of any type that is declared directly in a class or part of an object, while a parameter is a variable defined by its function that receives a value when it's called. So in other words, when we talk about attributes in coding, What we're talking about is it's data that's kind of like hard coded and attached to an object. Like, so for example, if I created a code object that described you, your date of birth would kind of be a fixed attribute. It's not like that's a piece of data related to you, but it's not a piece of data you can change, right? A parameter, on the other hand, is a piece of information we send to a program or a function or whatever that gets manipulated to do something else. That's the essential difference. So part of it is like learning terminology too. So when people throw terminology at you, you don't go, what? You know, and that's kind of what we're hammering here a little bit. All right. So there are some key aspects of working with DBScan, and one of the key settings is this. Okay, so I see it spelled one way in the code and a different way. You guys noticing that? Here it's EPS and here it's ESP. Okay. All right. So thank you, author, for the typo. It says the maximum distance between the two samples for one to be considered in the neighborhood of the other. So in other words, this normally we set to 0.5, but it doesn't declare really a maximum. And that's what they're saying in the second bullet. This is not a maximum bound, right? But this is the maximum distance between the samples. So like, in other words, if you have stuff that's clustered, it's saying that this piece, whatever piece of information I look at in the cluster, is at most this far away from another piece of information in the cluster. That's what it's saying. They say here that bullet number 3, this is the most important parameter to choose appropriately for your data set, and the distance function. The default value is 0.5, but they're telling us this is probably the most important one to tweak for this. The other one that's important here is the minimum number of samples. So the number of samples in an area or a cluster, or they're calling it the total weight. In other words, if the total weight for that point to be considered a core point in the data set. So it's really, you can tell, like those red ones, you could tell those were together, where the yellows were kind of on the outliers and the blue one was not, right? The minimum number of samples is 5, right? We talked about this before. And then this is one that you change to try to, what was it? Higher number, greater density, lower number, more sparse. The 5 is considered kind of like the minimum point. You can also abbreviate this one, so you can run DBScan just feeding it those 2 parameters if you wish. I don't think our examples are structured that way. I think they have all the parameters in there, but it is possible to do it with one brief little line of code if you so choose, right? If those are your key things. All right, folks, we're reaching the end of the PowerPoint here, which is kind of like, thank you, right? That we're almost done. But these are the things that we learned here today, what labeled and unlabeled data is and the difference, what we're talking about when we're talking about unsupervised learning, right? And it's basically the absence of having labeled data, and then what algorithms are using to cluster them. We use the k-means clustering model based on the distance formula mostly to do the clustering. And then we have the DBScan model, which uses a different algorithm and is better for highly clustered data, generally speaking. Right, so those are the key takeaways. What I'm going to do now is I'm going to stop this recording here. So our lecture for Unit 7 is done. So the video is now over.